just as we have m, the expected value or mean of the whole population is defined as j runs from 1 to ni and I runs from 1 to k, and mi as 1 by ni summation of xij, j runs from 1 to ni. We have things like this. There are k status and each one having population like this, and we have the total population as capital N. So, N is summation of Ni I equal to 1 to k. So, we have M defined like this and Mi defined like this, which is the expected value of mean of the whole population, and this is the expected value of the mean of each stratum. Similarly, we have sigma naught square, which is the variance of the whole population, precisely defined as there will be the double summation, and we have xij minus m square, xij minus m square, and here also j runs from 1 to ni and I runs from 1 to k. While just like this we have sigma I square defined as the variance of ith stratum, and that is defined as simple where mi is defined like this. Mi is the expected value of the ith stratum, and we take the difference whole square, sum it up over ni and divide with ni, so that we get the variance of ith stratum. Here we have another thing noted as sigma cap square, which is nothing, this denotes which is nothing but the variance between these stratums, or rather between each stratum. So, sigma cap square is defined as 1 by n summation mi minus m whole square into ni, and obviously here I runs from 1 to k. Just say that this is a weighted average, this ni is divided by summation ni is divided by here. So, this is the weighted average, and this gives the interstratum variance. So, you should remember these three things. Now, we will just find a relation between sigma naught square, sigma I square and sigma cap square. This is very easy. Just note that this can be written as I and j, x I j minus m I plus m I minus m whole square, and this can easily be written as 1 by n double summation 1 over I then over j, and we have x I j minus m I whole square plus 2 into x I j minus m I into m I minus m plus m I minus m whole square, just the square plus b square plus 2ab formula. Now, you can see that the first term is precisely nothing but the definition which we have written for sigma I square, provided we just replace this with Ni, and we can write it as 1 by n summation I equal to 1 to k Ni sigma I square, and this term we are just using the definition of sigma cap square. Sigma cap square is defined to be 1 by n summation Ni into Mi minus m whole square, the weighted average. And so, we could easily find that if we sum it up for this j, this Mi minus m square is summed up for Ni times. So, it obviously comes out to be, this term becomes 0 and this term comes out to be 1 by n summation Ni Mi minus m whole square. So, this will be precisely sigma cap square. And why this is 0? This term is 0. Why? Simply because of the definition of this Mi. Actually, if we make up the sum, this comes out of the j sum, and so this becomes summation of xij minus Mi by this. This is the, from here we can easily see that Mi Ni is equal to summation xij. This relation establishes that this is 0. This comes out of the j, and when this is summed up, this summation Mi summed for j equal to 1 to Ni gives Mi Ni, and this is summation xij, they are equal. So, this is 0. So, we can write that sigma naught square, which is the variance of the population, it is written as 1 by n summation Ni sigma I square for each strata plus sigma cap square. So, this is a very important relation which establish that this is a fixed quantity, the variance of the population, and if the variance between the strata increases, then the variance within the strata will reduce. Remember that this is nothing but the variance within the strata, which we defined as sigma I square. What is sigma I square? Sigma I square is the variance of the ith strata, and this is written as 1 by Ni summation xij minus Mi whole square, j is summed up from 1 to Ni. Okay. So, we can easily see that this is nothing but the variance within the weighted average of the variance within the stratum and variance between the stratums.